Welcome to This Explainer. Today, we are going to completely demystify how a basic computer vision system actually works. We're going to see exactly how a machine looks at what is basically just a giant grid of numbers and plays detective to stitch together a perfect panorama or help a robot navigate a messy room. It's a really fascinating journey, and we're going to build the whole thing step by step. Okay, let's dive right into this with a bit of a mystery. Think about the very last time you took a panorama photo on your phone. You probably swept your camera across this gorgeous mountain range, right? And your phone just seamlessly stitched all those separate frames together into one massive wide shot. But here is the crazy part. Your phone has absolutely zero idea what a mountain or a sky actually is. So how on earth does it know exactly how to align those overlapping pictures so perfectly? Well, today, we are going to solve that exact mystery by following the incredible journey of a single pixel. To get there, here's our roadmap for today. First, we'll look at the recognition game. Then, step 1, find, spotting the clues. Step 2, fingerprint, writing the code. Step 3, fit, solving the mystery. And finally, we'll wrap up with the deep learning evolution. So let's kick things off with section 1, the recognition game, also known as the spreadsheet of sight. And this brilliantly illustrates our starting point. Because to build our computer vision system, we actually have to completely unlearn how we humans see. You see, there's no actual image inside the computer. To the machine, it is just a massive spreadsheet of brightness values, ranging from 0 for pure black all the way up to 255 for pure white. So how does our pixels journey even begin? Well, it starts by finding an edge. We use some pretty simple math, basically sliding a tiny stencil across that grid to subtract the neighboring numbers. And where there's a massive jump, say from 42 all the way up to 200, boom, that's an edge. Literally every single computer vision detector starts by just figuring out how fast these numbers change from left to right and top to bottom. Now, once we have those basic gradients mapped out, we give our machine the ultimate detective's toolkit. We call it the F-cubed pipeline. It's 3 simple steps. Find, detect unique key points. Fingerprint, describe them with a compact code. And fit, match those codes across 2 different images to perfectly align them. Honestly, if we can master just these 3 steps, we have essentially built a working computer vision system from scratch. That brings us to section 2, find, spotting the clues. Or, as I like to think of it, looking for maximum surprise. Okay, so to spot our clues, we actually have to throw away like 99.9% of the pixels and keep only the truly unforgettable ones. And this perfectly captures the physical intuition behind the famous 1988 Harris corner detector. Imagine you're walking in a pitch black room, just running your hand along a flat wall. It's totally predictable, right? That is a flat pixel. It's boring and carries absolutely zero new information. Now imagine sliding your hand along the edge of a door frame. You just glide along the line, but the exact moment you hit a sharp corner, you feel a sudden, sharp change from every single direction. That right there is exactly what the Harris algorithm is looking for inside our spreadsheet. A point of maximum surprise where your prediction fails in every direction. A corner is totally unique, which means our machine detective can actually find it again. But wait, there's a bit of a catch here. If you take a picture and zoom way in on a sharp corner, it kind of melts into a smooth curve, doesn't it? So back in 2004, an ingenious algorithm called SIFT fixed this exact problem. SIFT basically builds what's called a scale space. It's kind of like squinting your eyes to look at the image across multiple levels of blur, all at the exact same time. This brilliant trick ensures our detective never loses track of our specific pixel's journey, whether the camera is zoomed way in, zoomed way out, or even tilted completely upside down. Moving right along to section 3, fingerprint, writing the code. We are crafting the wanted poster. So we found our highly unique pixel, but just finding it isn't quite enough. We have to give it a totally recognizable identity so we can reliably spot it in a completely different photograph later on. Enter the descriptor. A descriptor is essentially a tiny wanted poster for a patch of pixels. It doesn't just say, look for a person. It says, look for the person with the red scarf and the round glasses. Early algorithms like SIFT used a really rich 128 number vector just to describe the gradient directions around a pixel. But later algorithms, like Brief and Orb, simplified this beautifully. They basically just ask a few hundred rapid-fire yes or no questions about the pixels. Questions like, hey, is this pixel darker than that one? And from that, they create a tiny, hyper-efficient binary barcode. This is an absolute game changer because it allows the computer to compare millions of fingerprints per second at absolute lightning speed. Which leads us to section 4, fit,
solving the mystery by matching the clues.
All right, so we found our best clues and we've written up their wanted posters. Now comes the really fun part. We have to solve the mystery by actually matching the fingerprints between photo A and photo B. But matching is super tricky. I mean, think about a photo of a brick wall. You're going to have hundreds of corners that look almost completely identical to each other. If the machine just lazily picks the nearest match, it might just be a really lucky guess. So the crucial point is this magical number right here, 0.7. This is known as David Lowe's ratio test. Basically, it means a confident match absolutely must comfortably beat the runner-up by a wide margin. If your top winner is only barely ahead of the second best option, it's essentially just a coin toss, so the system literally just throws it away. We are ruthless here. We only keep the undeniable, rock-solid matches. But even with that strict ratio test, some false matches, basically some liars, are inevitably going to sneak through. So to fix that, we use a brilliant algorithm called Ransack. Ransack acts a lot like a democratic election. It randomly grabs 4 matches, creates a quick test alignment, and then turns to all the other matches and asks, hey, do you guys agree with this? It repeats this rapid-fire process hundreds of times and simply keeps the alignment that has the biggest crowd of supporters. The honest majority of matches will always outvote the few random liars. And the final winning alignment? We call that a homography matrix. It's just a fancy term for a mathematical formula that perfectly translates, rotates, and bends the perspective to fold one flat photo right onto another. And that brings us to our final stop, Section 5, the deep learning evolution. This is when the priors became parameters. Now, you might be wondering, did the AI revolution in deep learning just come along and completely wipe out all this classical math? Absolutely not. Just look at this continuous 3-decade lineage. Deep learning didn't replace these core ideas at all. It just learned them. It's wild. If you train a convolutional neural network from scratch today, its very first layers will spontaneously grow edge and corner detectors that look exactly like the math we were doing back in 1988. The priors literally became the parameters. Modern deep learning tools like Superpoint and Loaf-Tier, they're still executing this exact same 3-step pipeline. They just use neural networks to find and fingerprint the key points directly from the raw data. And that makes them incredibly robust, even when they're trying to match completely blank, textureless walls where the classical methods would totally fail. And the coolest part? This find, fingerprint, and fit pipeline is silently powering your world literally right now. When your phone seamlessly blends that beautiful mountain panorama, it is running this entire pipeline in under a second. When an augmented reality app pins a digital character to your real-world coffee table, or a self-driving car tracks its exact motion through optical flow, or even when you just do a reverse image search on Google, they are all playing this exact same game. They're discovering surprising corners, writing tiny barcodes, and fitting them all together. So we return right back to where we started. Your phone doesn't actually know what a mountain is. It just knows how to perfectly track the journey of a single pixel. It knows how to spot a surprising jump in numbers, compress that surprise into a tiny wanted poster, and lock the geometry perfectly into place. Next time a robot navigates a room or your phone stitches a landscape, will you see the hidden game of pixels being found, fingerprinted, and fit together? I hope so. Take a moment to appreciate the incredible, invisible detective story happening right in your pocket. Thanks for learning with me today.